So this problem which we are going to discuss is there are many names to it, but basically it is related to fracture mechanics. And here what we have is, usually we have a cracked sample, right? So there are many different types of specimens which are used for measurement of fracture toughness. One is this, which is CT specimen. So looks like this, okay. And then we have a sharp crack here because of fatigue, and then you load it like this, and then the crack propagates, and then you find out the fracture toughness. So you either find out K1C or J integral J1C or J versus delta A curve and all those things, okay. So in order to do the simulation, sometimes it is important to understand what is happening exactly at the crack tip. So not exactly at the crack tip, but very close to the crack tip. And knowing that is not possible experimentally, because at the crack tip you cannot put any measurement tool, right? And a lot of things are happening there where theories are not working. So for instance, if you remember our previous course on mechanical behavior and testing of materials, so there we spoke about crack being a singularity, and there is a plastic zone associated to it, which looks in mode 1, it has a shape of this, right? So so this is the shape of von Mises stress, and when von Mises stress is higher than certain value, which is your yield strength, then you can say that the plastic deformation has started. And because the stress usually increases as you go near to the crack tip, so according to the theory of elasticity it should reach infinity, but it will get truncated at some point where the yielding hits, and then you have hardening rule and all those, and because of that you will be having a plastic zone, right? So elastic theory, which was Irwin's idea, so basically the stress definition was based on a stress intensity factor, which was following this equation, is not valid in the plastic zone because this is coming from the theory of elasticity. So what is valid in plastic zone is J integral, and that also has some problems. So there is a zone where even J integral cannot define the stress and strain relationship, and that is somewhere inside this zone, and that we call process zone. So that we have not discussed in our course because that's not the part of our syllabus, but the simple idea is that there is a zone which is very complicated, right? And we do not know what happens to the stress versus strain relationship. So basically we do not know how the stress and the strain are related there. So we define a zone and we say that if that is very small, if this thing is very small, then we can still deal with theory of elasticity, right? So that was your that is why you get that criteria that your thickness of the specimen and the initial crack length should be smaller than 2.5 into K1C by sigma naught whole square. So it should be 50 times smaller than the plastic zone radius, right? So this criteria is there when you calculate stress intensity based fracture toughness, so that the plastic zone is very small. So you can say that the plasticity where the theory is not valid is very small and it can be ignored. Then you come up with another criteria which has a broader zone, so it can include plasticity, but then you again have a smaller zone inside it where still, you know, things are not happening. Why things are not happening? Because what is plasticity? Plasticity is that you have a stress versus strain relationship, and there is a part of strain which is permanent and irreversible, and that doesn't follow linear relationship with the strain. It follows some other relationship with the strain. Okay, so it is non-linear. So you treat it as non-linear elasticity in some cases. In some cases you can use it as elastic-plastic relationship. But then at the crack tip, so here at the crack tip, you will also be having void formation at some point, right? So you have damage there, and this discontinuous damage is not included in the theory of plasticity. So that cannot be taken care of by J integral, right? So which means that there is an area or there is a volume where the existing stress versus strain relationship doesn't work. Just hold on a second.
सर बोलो गेट पे लगा है ना हमने क्या लगा है वहाँ पे उद्घाटन का भी बोर्ड लगा है ना गेट पे उसी के देख लेंगे.
So this volume, in this volume we have very large strains. Okay, very large strain, and so large strain meaning that we cannot just use the normal strain formulation, which is this. So del uj by del xr. So this we cannot use. This is applicable only when the strain is very small. So it is called small strain theory. And when we have very large strain, then there are higher order terms. So you have higher order terms of this kind of expressions which you will have to include in the strain equation. So that's why that is called finite strain or large strain theory. So that happens at the crack tip, that you have a lot of large strain phenomena happening, and then there is damage also happening. So you have discontinuous media, so it is not continuum anymore, and therefore these equation, whatever equations we have which can define crack, the stress distribution and strain distribution at the crack, is not valid in this zone. Okay, so that we call as process zone, and if that process zone is very small, then we say that fine J integral is okay, similar to what we do with the stress intensity factor formulation. So in order to find out what really is happening at the crack tip, and not in the process zone but in the plastic zone, let us say, we need to find out how the stresses are and how the strains are at the crack tip, right? Now we have to look at what problems we will come into if we try to model it. So modeling is one escape route, and it is also an accurate way of finding out the stress and strain relationship at the crack tip, because experimentally you cannot do anything. You cannot put an extensometer at the crack tip, or you cannot in any way you cannot measure the strain or stresses at the crack tip, exactly at the crack tip. You don't do that, right? So when you do the experiment, you basically apply force and you measure that force, and then you measure how much is the specimen opening up. Okay, so after some time it will open up with certain amount, and then you will measure this opening, which is called crack tip opening displacement. And there are various ways of measuring how much the crack is opening, and from that you find out all different parameters which defines the material's resistance towards cracking. But you cannot find out the strain by experiment, right? And also stresses by experiment at the crack tip while the test is going on. So one way of doing this is by finite element simulation. And when you do finite element simulation, you should know that what is the size of your process zone, because there the stress and strain values will be wrong. That is number one. And you also have to know that you have to get the stress strain at a very small volume at the crack tip. Okay, so usually if you look at this volume, so this ligament is going to be much smaller, much larger than this zone, right? So we have established in theory of elasticity that it should be at least 50 times higher than the plastic zone radius. But for J integral it will be even smaller. The plastic zone will be even smaller. So that small area, if you want to find out the stress and strain, you will have to have very fine mesh there. You will have to have very small element size. So if your plastic zone is, let us say, 1 micrometer, so you cannot just have one element there. You have to have at least 100 elements there, right? So that small amount of meshing becomes very complicated. So you will have very huge number of elements in your calculation, and this will be a burden on your computation. So what is, can we do a trick here? Can we do something about it so that we don't really have to model that many number of elements and we still can find out what we want to find out? So we are going to entertain one of those tricks, which is called modified boundary layer problem. So that's just a fancy name for this, and sometimes it is also called small scale yielding model. Also another fancy name for this, but it is actually a very simple idea, is that you take this piece of material out and just model that thing. Okay, so instead of modeling the whole specimen, loading and other things, you take a circular piece of material out. Okay, so you make a circle at the crack tip and you take it out and model just this. And in order to model this, you need to know that what boundary conditions you will have to apply at the boundary of this circle which you have taken out, right? So you need to know what is the boundary condition, and you need to know that the process zone and the plastic zone is contained within this circle. So the radius of this circle has to be not very large, but it should be larger than your plastic zone. Okay, and when you ensure that plastic zone, so not just larger but sufficiently larger, so at least 10 times larger than your plastic zone, not 50 times but 10 times. So 10 times is still smaller. Okay, and when you do that, when you ensure this condition, then you are ensuring that your boundary condition is going to follow theory of elasticity, right? Because plasticity is contained within, so you can apply the boundary condition using the theory of elasticity. And I will just tell you what the boundary conditions are without going much into the detail. So on this circle, and one more decrement in the modeling can be done by making this circle a semicircle and using the symmetry. So instead of modeling the whole circle, you just have to model half of it, and on the boundary of this you will be defining boundary condition in terms of displacement. So u1, u2, and then you take another point and there you define u1 and u2, and you take different points, and on that you keep on defining u1 and u2s. Okay, and once you define that and apply that, it's all good, and then you can model it, and then you can find out what happens to the stresses and strains in the plastic zone and which is not falling inside the process zone. Okay, so the equation which is used to describe the displacements at different angles, okay, So it has to be a function of theta, can be written in this form. So I'm not going to derive this equation, but it comes from our stress intensity factor relationship with the stress and strain. So 4 mu minus cos theta, and then your V is k into 1 plus mu by E root over r by 2 pi sine of theta by 2, 3 minus 4 mu minus cos theta. Okay, so you plug in different values of theta and you can get the values of u's and v's which you have to apply. So far, is it clear for you? Elastic component, no, I didn't get it. So we are ensuring that this circle which is coming out of the system, so this is my specimen, and from this specimen I am taking a circle out, and what I am ensuring is that the boundary of this circle is in the elastic region. So what I am ensuring is that the plastic zone is inside this circle. So what is your question again? Yeah, so that's how, because we are ensuring that the boundary is in elastic region, we are able to use this equation. You don't see any parameter which is related to plasticity in this equation. Okay, so K is a stress intensity factor that comes from the theory of elasticity. Poisson's ratio is mu, and then r is the radius. Okay, so this distance is r, and apart from that you have just theta. So there is nothing. There is no strain hardening exponent, there is no yield strength, nothing which defines plasticity because the boundary falls in the elastic region. Okay. So what you do is, for instance, you want to model some material, so stainless steel 304, let's say, and you know that the yield strength, initial yield strength is 200 megapascal. Okay. So you will find out that what will be the value of, and you are applying, let us say, a stress intensity factor of 20 ampere root meter. This is what you want to apply. Okay, so you can calculate the radius of plastic zone based on your plane stress plane strain formulation. So safer would be to take the worst case, which will be plane stress. So take 1 by 2 pi, and K1C is 20 divided by 200 whole squared, right? So K1C by sigma not whole squared. So that becomes 1 by 10, so 1 by 100, so 1 by 200 pi. So this is going to be your plastic zone radius, and then multiply this with 10 and find out that how large of the circle you have to take out. Is it clear? Okay. So once you have made this model, then you know this is the boundary condition you have to apply, and now we will see that how can we apply these boundary conditions. So we are switching back to now the modeling part. I hope the theory part is clear, and in this problem we just want to understand that a little complicated modeling, a little complicated boundary conditions, how do we do it? Okay, so I want to keep the annotations and stop presenting. Okay, and let us come to the modeling part. Where is it? Okay, so I have already made a lot of things in this, but we will go one by one. So this is that circle which I was talking about. So it's just a circle with certain radius. So we can see what is the radius here. So you can we can measure it, and the radius of this semicircle is 8 millimeters. Okay, so then you go to property module and you define your material. This is similar to what we have done previously, so I am not changing the resolution here. So just giving the elastic property, so you give 200 blah 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 Poisson's ratio, and then you give plasticity. So we calculated for, so it will be how much for 200 megapascals, 1 divided by 200 pi, 1 divided by 200 pi is 2 into 10 power minus 3 meters, so that is 2 millimeter. So our plastic zone is going to be 2 millimeters if we keep our yield strength as 200 megapascals. Okay, I'll keep it 200, plastic strain 0, and I am only giving 1 point, which means it is elastic perfectly plastic kind of material. So the hardening is not there. It is not softening, it is not hardening. It will just keep on plastically deforming at the same value of stress. The strain will keep on increasing. This kind of formulation causes problem in convergence, because at one value of stress you have infinite number of strain values corresponding to one stress value, right? So usually we should avoid this elastic perfectly plastic modeling, but let us see what happens. And so we have given elasticity, plasticity, nothing else is required. So we are done here in the property. So let me assign this to this circle. So let us make a section which is homogeneous, solid, plane stress, plane strain, anything is not required. Done. Okay, now go to assembly. We have already brought in to the assembly step. You just make a step and all the default values. Okay, so there is nothing fancy here. So we are keeping the step formulation same. In interaction formulation we are not doing anything. Interaction formulation we have not done any example so far, but basically here we can define multi-point constraint kind of things, and we can also define friction. So if we have two things which are sliding or contacting each other, so that friction and other things are defined in interaction module. And then we go to boundary condition. Okay, and if you look at the boundary condition, it looks like this. Do you see this on a screen? Do you see anything on the screen? You see too large. Okay, so let me change the resolution to 19,080. Keep changes. Okay, so what do you see? Is it not here? So this one. Okay, so you see something on the screen? So you see these arrows. So orthogonal arrows are defining U1 and V1. So U1, V1, U2, V2 at different locations. Okay, so this is how the boundary condition looks like, but the question is how will you apply it? How will you do that? Okay, so some of the boundary conditions are going to be very simple. So let us go to boundary condition and delete all those which are not required. So Y symmetry we have to keep, and apart from that we don't have to keep anything. So we'll just delete all the other things. So where is my boundary condition? Here. So we delete all these things. Okay, still there is one. Okay, So one boundary condition which we have to keep is that this section has to be y symmetric, right? So the ligament has to be y symmetric because we are modeling half of the circle. Okay, so we have to select not this, we have to select this half. Okay, so this has to be partitioned. So instead of partitioning the cell, we have to partition an edge, specifying parameter by location, edge, done, and no, there, create partition. Okay, and now the boundary condition is the y symmetry. So we take the ligament, which is this and this and this and that and that and that and that, and done, and okay. So now do you see which part I have given the boundary condition? The right one, right? So the left one can open up because that's the crack opening part. The center of the circle defines the crack tip. Okay, so one boundary condition was very easy and that has been applied. The rest of the boundary conditions are not easy, and that we will try to apply some coding. Let us say if that works well, and before that we have to mesh it. Okay, and we have to mesh it in a very nice way so that we get these meshing lines at predefined angles. Okay, so in order to do that, what we will have to do is we will have to assign local element size. So we take this inner circle and select that and say that I want 20 number of elements there. You can increase it, you can decrease it. Okay, so let us say that I make it 50 and then apply. So it will delete all the meshes, and then I want to keep the same number of elements on the outer side also, so that I will maintain the same angle. So it will be 50 there also. Apply, delete meshes, and I want to keep 50 there also. So 50, and I want to keep 50 there also, 50 there also, and 50 there also. So 50. Okay, and now I will mesh it and let us see how it looks like. It looks okay. Okay, so this center part is a little bit awkward, so there we have to do even proper partitioning and meshing well so that it looks good. So for instance, here we can do something. So here we can do and then we take this one and flip it. So and then so we can decrease it by size. Maximum is 0.5, no, maximum is 2.7. So maximum 0.5, let us keep minimum as 0.05, and then it looks bad, so it should be 0.1. Looks okay. And then let us try to mesh this part. It looks okay now. Okay, so now we have got this proper mesh, and we know that these things are at certain angle. Okay, the outer boundary is divided into 50 pieces, right? We must have 50 number of elements on the outer boundary. Do we have them? So 1 2 3 4 5 6 9 10 and 3 10 20 and 3 and 1 30 and then 3 and 3 and 1 40 and 3 and 1. So it looks like it's 52 or something, but it shouldn't happen. So if we we have to find local seeding, number of elements 50. So there will be 50 elements, should be 50 elements. Okay, but we can check that out, we can ensure it. So so now we want to know, we know that it's even division of a semicircle of radius 8 millimeter, and we want to find out that how much is the angle between two lines. So that you can analytically calculate, or you can calculate from query, and you can query by picking face of 3 points. We'll take 3 points. So the vertex is somewhere at the center, which is this, and second vertex is that, and third vertex is this, and so the angle is approximately 88.2 degrees. Okay, so 88.2 into 50 is how much? No, that's too high. This doesn't look like 88 degrees. It is giving me some different angle. So I think we have to define the 3 points in a different way. So 2 and 3, yeah, so now this is 3.59, so that looks like it. 3.59 is approximately 3.6. So 3.6 into 50 element is 180 degrees, so this is okay. So our each division of this, so each arc is at approximately 3.6 degrees. Okay, so we know the value of theta now, and we should also know a little bit other dimension, but before that we will have to calculate that how much will be the u1 and v1 values which we have to apply at each point. Okay, are you getting what I'm saying? So for instance, here how much u1 v1 you have to apply, there how much u1 v1 you have to apply, and so on and so forth. Okay, so that calculation we'll have to do in Excel, or you can do in some other programming language. Okay, so our division is at 3.6 degrees, right? So 3.6 degrees, and then we have to keep on adding to this 3.6, and we have to go until it reaches 180. So so 180. Okay, all right, so now we have the angle, and we want to find out the x coordinate and y coordinate of the point or the node where we have to apply u1 and v1 value. So we can simply get it by r cos theta, r sin theta. Can you see it? Okay, so this is theta, then x and y coordinate of the nodes we can get by simply doing x is equal to r cos theta and y is equal to r sin theta, right? So we will get the coordinate where we have to apply the boundary conditions, and then we have to calculate the values of u's and v. So u and v, which is displacement in x direction, displacement in y direction. Okay, so this is simply gonna be 8 into cosine of the theta, but this theta is going to be the radian value. Okay, it will not take the degree value here. So before doing this, let us insert a column and change it to radian values, and so this will be this into pi divided by 180. So now we have the radian value, and now we can write r cos theta is equal to 8 into cosine of this column, so which is b 3, and this will be is equal to 8 into sine of B3. And so we have x and y coordinates, and now we have to calculate u's and v's. And for the plastic zone which we calculated for 200 megapascal, we calculated that for K is equal to 20 ampere root meter, right? So m to the power 0.5. And for this value of K, we have to calculate u's and v's. So what was our formula? Our formula, so have to see it again. It should be here, right? Yeah. So the formula for u was K into 1 plus mu divided by E into R by 2 pi into cos theta by 2, 3 minus 4 mu minus cos theta. Okay. So u is equal to K, which is stress intensity factor, and we have to keep the dimensions in check. Okay, because that can create a lot of problems. So the u which we will be getting here will be in meters, because our K is in ampere root meter and elastic modulus is in MPa. Okay, so that will have to change to millimeters at the end. Okay, so this will be 20 into 1 plus 0.3, so we can simply keep it 1.3 divided by elastic modulus is 200 gigapascal, so 200,000 into, now we have R by 2 pi, so R is 8 divided by 2 into pi, and this thing into function of theta, which is cos of theta by 2 and then into 3 minus 4 mu into cos theta. So this into 3 minus 4 into 0.3 minus cos of B3. So this appears to be in millimeters only, or what? So MPa is getting cancelled. Then what is happening to root meter? No, but that is not there. Okay, so it appears that it is in millimeters. If not, we will see. If it is in meters, it should cause. No, it could be. Okay, so we'll have to see, because we are at a very small angle here. We are at a 0 angle, and 0 angle, our displacement in x direction should be very low, and in y direction it should be very high. So our v value is similar to this. I'll just copy this thing here, and instead of cos has to be replaced with sine, and here it is cos only, and everything else is same. And then so we get the values of displacement. So at 180 degree the value is approximately 0. So this is okay. So these are the values of u's and v's which we have to apply at this x value and this y value. Okay. So now we have done our calculation. Now how we will apply in this boundary condition? So for that we have to use a coding system, and so we have already a code here, and this code you can write by using, so because of resolution, I cannot see the name here. Okay. All right. So we will write this code again, and you can actually write. So in this code, the whole calculation of ux and uy is also done inside this code, but this can be done outside, which we have done already. Okay, and then we will simply apply this to our boundary condition. So let me explain this. Can you see this code? But can you really see the text also? Okay. So how do we increase the size? Zoom. Control plus zoom. My mouse wheel up. Okay, so do you see anything now? Okay, so here you see the value of K, which is stress intensity factor, and this code was for 100 megapascal root meter. The value of shear modulus is in terms of megapascal, so 70 gigapascal, and the value of radius is 8 into 0.001 is meter. So radius is changed into from millimeters to meters. Okay, yeah, that's what we will have to do. So we have done even number of mistakes, and then Poisson's ratio could be 0.3, 0.33, it doesn't matter. So 3.4 mu, which we have calculated, so like 3 minus 4 mu into cos theta, that thing is calculated before. Okay, and then you take the model name, instance name, and then you calculate. So let us say the value of theta in our case was 3.6 degrees, right? So P starts from 0, and at the end it gets updated by the angle by which you have divided the outer circle, which was in our case 3.6. No? So it will get updated by 3.6, and so the angle in radian will be calculated using this formula. And then instead of calculating x and y, you can simply write u's and u1 and u2 or ux or uy using the formula which we have just done in our Excel sheet. Okay, and we can assign the boundary condition in two different ways. One way is by using the nodes, and another way is by using the x and y coordinate. So when we use x and y coordinate, we will use the calculation of x and y's, and when we use the nodes, then we can use the node formula. Okay, so let us try this code first, and then we'll try to switch it to the coordinate based coding. Okay, so now we have to see in our model that the node are starting. So usually what happens that in Abaqus, when you do this kind of meshing, it assigns the numbers to the node in a particular order, and we have to be sure that they are in order. Only then we will be able to assign the boundary condition based on node number coding. So let us find out that what is the node number here, and there it will not be possible to find out the node number because there is a vertex also. So it will simply tell us the vertex, which is 2, and the coordinate value. But if I find out this one, then it should give me the node number, which is 113. So this is 113, and this should be 114 or 112, 114. Then this should be 115. So 115. Oh, do you see it? It is getting written in the here in the bottom message box. Okay, so it is starting from 113, but the node number here is not 112. I'm pretty sure of that. So we will have to find out what is the node number there, but let us see what is happening for others. So 113, 114, 115, and so on. So here we should be reaching how much? 113 plus 50 is 163, no? So 161. Why is that? Yeah, we are leaving one here, one there. Okay, so it is starting from 113 and going to 161. Okay, and then we need to know this node and that node. How do we know this node and that node? Is it 112? Can we check? No. Can we find out can we select a node? So node, no. If I select, then I do not know. But we can see in the element what are the nodes which are there. So this is element number 100, and there are 15, 1, 5 and 113 number of nodes. So 113 is there, that we know that is 113. So 112 is not here in this element. So there is 1, 5 and 15. 1, 5 and 15. So, and 2 are common. So if I check these elements, 2 of these are going to be there. So if I check this one, then we have 1, 15, 1, 1, 2 and 4. So out of these two, 15 and 1 are common. So this is, these two nodes are either 15 and 1, and this one is 113. So this is 5. This is node number 5. And similarly, so it's not in certain order. So we'll have to assign on this node and that node manually, and for the rest we can write a code. Okay. So here we will start from 113 and we will go till 161, but it will never go to 161. Will it go to 161? So I do not know, but we can check. So we go to Python shell and see for I in range of 1 to how much? I always forget the syntax. So 1, 2, 3. Let us say 1, 2, 3 colon, and then just print the value of I, and then indentation error. Okay. End. Oh, there is no end here. So So 1 and 2. So it is starting from 1 and not going to the final value, right? So 161 it will never reach. So we have to write 162 so that 161 is also included. So it is going from 113 to 162, and then theta is there and all the calculations are there, and ux and uy are getting calculated. Now for node I and I plus 1, so that means 113 and 114. This is how it selects one node. So it finds out the node. If you give two consecutive nodes, then it will find out, it will take I as that node. So node is selected and then we make a set. So if you want to name something as set 1 or set 2, so you take this string plus add this string of I. So I will be 113 for the first one, so it will form set 113, and the name of the boundary conditions will similarly be BC 113. Okay, I don't know why the nodes are written twice. It's the same, it's redundant. I don't think it is required. So, and then the region has been selected as nodes is equal to node 1, name is equal to set, and then in the model 1 the boundary condition name is BC, which is BC is defined as a variable which is the string BC plus the value of the I index, okay, and it is being applied in step 1 in the region, and region has been selected as the node and the set, okay. U1 and U2 are the value which are going to be set in the boundary condition, okay, and the values of U1 is going to be Ux, which we are calculating here, and U2 is going to be Uy, which we are calculating there, okay, and then the value of angle will be increased to whatever value was initial, which is 0 plus 3.6, and in the next one it will be increased by another 3.6 value, okay. Is this understood? Alright, so we don't need this part. So edit, and where can I make it? Where can I change it to comment? Comment and comment. So toggle single line comment. Okay, and this also has to be commented, and done. Okay. So what are we doing here? We are assigning the boundary conditions to node number 113 to 11162. So let me save it somewhere. So we will go, where are we? This is in, oh, this is somewhere else. But it doesn't matter, but we should put it in the proper place. So MM3, and then create another folder, SSY, okay, and so now let us save this code also there. Where is it? Here, and then SSY, and the name of this code could be anything. I'll just write it, and then so we don't need these sets are invalid. I'll just delete them. Anyways, even if these sets remain, it's not going to be a problem because our set numbering is starting from 113. So I don't see any conflict with the existing number of sets, and the boundary condition has already been deleted. So when I run the code, what are we expecting? We are expecting that there will be new sets here starting from 113 to 161, and there will be new boundary conditions starting from BC 113 to BC 161. This is what I am expecting. It might not run, but let us see. So run script, and something has happened. So you see we have set 113 and it goes until set 161, and similarly boundary condition 113 and it goes to 161. And if we look in the boundary condition, you see that the boundary condition has been applied on different number of nodes. Okay, do you see that? Okay, so now we just have to confirm if PC113 has been applied to the right set. So we are not able to see it actually. If we go in the mesh, can we see this? No. Okay, but it looks like, so 161 looks okay, but here it doesn't look like it has applied anything to, no, it's wrong, something is wrong. So I believe this is because we are taking I to I plus 1 in a wrong way. So something is not working properly. So theta is getting changed to radian. That is okay. Instead of I to I plus 1, so this we have to check. So this we need to confirm. So the internet is very slow. Instead of, yeah, nothing can be done about this. Okay, so I hope it will come in some time. Till then, we will have to delete the boundary conditions. So I just want to confirm that I believe that it is the selection of number of node, which is why it's assigning boundary condition after one node. I'm pretty sure of that, but I just want to confirm it. So it looks like the internet has given up on me. So I'm gonna then try only hit and trial. So I'll do what? I'll just change it. Instead of writing I to I plus 1, I'll write I minus 1 to I. Okay. So then what will happen? I minus 1 wouldn't exist. Why not? It should exist. So let us see. So file and script. So now it works. That's good. So we are starting from 113 and there is no boundary condition which is at a weird place and it's going till there. Okay. So what I was thinking was right, that instead of I to I plus 1, so you have to give consecutive number of nodes, but I value is starting from 113, so it should take one previous, so 112 and 113, then it will select 113. Okay. So now we are done, right? So all those things we have assigned. Now we have to assign one value there and one value there, and after that we are good to go, right? So let us go to boundary condition and do it manually. So BC and start and displacement, and we select in viewport, we select this vertex, and done. We say U1 and U2, and I want to see what is the value for an angle of 0 degree. Okay, so an angle of 0 degree, you know. So but that calculation we did a little mistake there. So in this code we have calculated for theta is equal to 0. Theta is equal to 0, right? Oh, no. So theta is going to increase. No. So for node 113, theta is not 0. Theta is not 0. Theta is starting from 3.6. Because 0 we are assigning manually. So this has to be 3.6. So it will begin with 3.6 and it will stop at an angle. So it should be stopping. So we started previously at 0, but if we start at 3.6, it should be ending at 180 minus 3.6 degrees, right? Because there is one node which we are leaving at the end also. So we'll have to do it again. So BC 113 216 12113, delete, and run the script again, and this should be okay. And now if I get the value of the theta, which is P, it should be 180 minus 3.6, no? 176.4. So what is the value of P? P is 180. How come it is reaching to 180 value? Oh, because it is going to 162, but it is not catching that. Okay. And the first value of theta, that we cannot find out. Okay. So the value for theta is equal to 0 has to be assigned there. So what is the value of theta? What is the value of u as and v for 0 degree is this, and here what we had to do is r should have been changed to meters, and then it will come in meter, and then at the end you change it to millimeters. So this will be 0.008, and where else do we have? Nowhere else, no? So this whole thing at the end, this is coming in meters, so this into 1000. So now it's okay, and there also we have to do 0.008, and at the end you have to make it millimeters. Okay, so this is the value of u1, which is 0.0013069. So 0.001307. So create 0 degree, this vertex, done. U1 was 0.001307, 0.001307, and U2 is 0. So 0, and we have to create BC is equal to 180, which is at this vertex, and here we have to put the value for theta is equal to 180, which is approximately 0 in U1 and 0.0046 in V1. So 0.0046, and U1 it will go to 0. Done. So now we have assigned all the boundary conditions. We go to job and create and write it SSY node paste and done. So give some amount of memory to this and submit. So did you guys understand anything today? Yeah, so coding is piece by piece instead of so I will give you this piece of code, but whatever you want to do, no, so I'll tell you. So this job is submitted, but let us say what we have done in this coding is that we need to know what we need to know that how do we assign the value of u1 and u2 to a certain node, right? This part of coding you do not know, but writing a formula and writing a for loop, that part is clear to you, right? Okay, so these are piece by piece things. So for instance, if I want to do all the thing in coding, I can do it, but the best way to do it is, so I just recorded this session in the coding part, which is in our work directory. Where is it? Here, SSY, Abaqus macros. So I open it. So you know, I have told you about Abaqus macros, no? So it records your session in the form of code. So whatever we have done has been recorded. Okay. So we need to find out that place, and actually for masking I was looking for that, yeah, this file. So you need to take this line, copy it, and before recording the session, go to the Python shell in Abaqus, which is in the downside, and just paste this line which we got from that article, which is named Learn Abaqus Scripting in 1 hour. I don't know why it is not getting pasted now. So Control V and enter. So this is session.journal options set value blah 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 to coordinate. So instead of masking in the code, it will give all the values. So you see here, no, that it is selecting some of the edges, some of the faces, some of the nodes with a masking scheme. So that will not be there if we use that command. So now what we want to do, we want to find out that how to assign a boundary condition to certain noding system. So there is a node and we want to assign boundary condition to that, and that part of coding we want to know. Okay, so for that we need to have a meshed part in the assembly. So we go to our part module, which is here, and we make it dependent, but then all the meshing will be gone. No worries, we'll do it again. So where is my assembly? Is here, instance is there, so I'll make it dependent. Okay, and then we go to part module, and now we go to mesh module, and now we have to assign the seeds. So select all this. So this is partition, so select all the edges, and done, and none, and 50 when number 50 apply, and okay, and just mesh this thing. Yes, okay, so done, meshing is done. Now now it is also divided into 50 pieces, and if I make it, so now I want to make it, we go to mesh and create mesh part. So I make an object out of this mesh. Okay, and then I bring it to assembly, and from the assembly I remove the previous part and I bring in the meshed part. Okay, so now it is there. So now I will be able to see the nodes even when I apply boundary condition in the graphical user interface. So, and I want to know what is the syntax of doing that. So let me delete all the boundary conditions. Delete, yes. Okay, and I want to know two things. I want to know that how can I do it based on coordinates, and how can I do it based on the node numbers. Okay, so let us start the macro manager, and start recording, and then go to boundary condition, and then create a boundary condition and name it trial, which you want to find out for the syntax. Okay, and continue. And you want to know that if you select it using the node, then you see the set number. You can also name it set trial, and then select this node and then say done, and then the value of u1 and u2 you can write something which you can notice. So 55555 and u2 is 66666, and OK, and stop recording, and then go to your work directory and then open the macros and look at macro 2. So this small piece of coding will tell you what is the syntax to apply the boundary condition on a specific node. Okay, so session part is not required, so that part you can simply delete. Important part is to take the assembly, and this is the line for assembly, and then take the nodes, because so this line is coming because I have created a part which is just mesh. It's not an object, it's a meshed thing. Okay, so it is taking all the nodes in it, and then you see that it is selecting node in this form. And if you look at the thing here, and if you find out that which node this one is, so this one is the node number 64. Okay, so this is node number 64. And if you now look at the macros, you see that in order to assign something to node number 64, it is taking 63 and 64 in the consecutive order. Okay, and then this line is required for the region, and this is the line required for assigning u1 value, which was 555555, and 66666 for u2. So what you have to do is you just have to copy these lines, Control C, and you create your own Python code new and paste it there, and then you go in the front and you see that do not delete the following import lines. So this is what you need for your Python code to run in Abaqus. So you put that in the beginning, and then you import all the libraries, import section and blah and blah and blah. So copy all those and paste it just after the import main. Didn't these things, so go to this is commenting, where is indenting, so decrease line indent. And so now you have the import section, Abaqus important lines, and then you have the syntax for assigning the boundary condition, right? And what else you need? So these are all done. Okay, so these are the lines which you will need, and out of these lines you will not need these lines every time, but you will need these lines in a for loop. Okay, so separate these lines, and from here you start writing a for loop. So for I in range, and then whatever node number was there, so 113 to 162 colon, and then now you have to create an indent here. So go to indent, increase line indent, and now here what is there? So you need the value of u1 and u2, right? So how will you calculate u1 and u2? That formula you have to write. So you need to write u1 is equal to formula, u2 is equal to formula, whatever formula you are using. So you can calculate u1 and u2 and whatever things you need for that u1 and u2. So you need angle theta, you need x and y and whatever, all those things you have to bring into your code. So once you have defined what u1 value and what u2 value you are going to use for different I parameters. So the index of this for loop is changing based on the angle, right? So you have to keep that also. So theta also you have to keep. So theta is equal to whatever. It starts from 0, then 0. If it starts from 3.6, 3.6. Okay. And then u1 and u2 and then you have to do a certain string based coding. So you have to define set is equal to string set plus string value of index, and then the boundary condition you make that also as a variable bc plus string I, and then you see here instead of name is equal to quotes set trial, you just write the variable set, okay, which means string set plus I, okay, and then instead of this bc trial you write the variable bc, and step 1 instead of u1 you write, so don't write u1 here because that is a Abaqus variable, so that will be conflict. So you write here u1 is equal to the variable ux and u2 is the variable uy, okay, and this is done. That is it. This is what you have to do. It's not a very complicated piece of coding. Is it clear? Do you understand what we did? Okay, so this was how do you apply the boundary condition, and you can do a lot of other things, so including everything. So you can do partitioning, you can do, for instance, you want to make 100 number of steps. So instead of making 100 steps by going in the step module and creating here and doing all that thing, what you can simply do is just record one step making thing. So let us do that just for the sake of it. So I create another macro and continue, and now I have started recording, and you create step 2, okay. So it is creating step 2, which is static general, continue, and then you're giving a time period, so you can change it also. So give it a value of 6, and here you give it 0.06. This is just for example, it's not necessary that you make it 6 or something, it's just for example. So give it 0.6, make it that number of increment, and okay, and step 2 is created. Now stop recording, okay, and now you go to macros and see what happens. What is the code to generate a step? So this is the code to generate a step, right? This is the line which you need. You don't need this line. Session viewport is for the viewport, so you don't need this line. You just need one line to create a step. So you copy this, and let us go to this previous code where we have done what we have done, and paste these lines, and I'll comment all these sessions. So I will comment it out. So single line comment. So my boundary condition thing has been commented. So in this code now I am only getting assembly and nodes, and then I have this line which is creating a step, okay. So model 1, and it is creating a step which is preceded by step number 1 with a time period, maximum number of increment, initial increment, minimum increment, maximum increment values of this, and I can code it, okay. So I can just write a for loop for I in range, and let us say I want to make 100 steps. So I'll start from 0 and I'll go to 100. It will make 101. So I'll go to 99, then colon, and then what do I need to do? I need to define a string to define step name. So that will be my step is equal to string step, and step 1 I already have. So I want to create from step number 2, okay. So I will start from 1 and then plus stri. So this has become a variable, and then the previous one also has to be a variable, right? So previous one will be p step is equal to the same thing but with I minus 1, right? Because step 2 is preceded by step 1, step 3 is preceded by step 2, and so on and so forth, okay. And then make an indent here also, and then instead of step 2, which is the step you are creating, write the variable step, and in the previous you write p step variable, and rest of the things, if you want to make those also as a variable, that is your call, but in this example I'm going to keep those things constant. Okay, and rest of the things are okay, I believe, because I have changed the assembly, because so part 1 mesh, so this is what I have to do. So this is taken, so node is actually, instance name has changed because I imported that what do you call it, meshed part, no? So instead of part -1 it has become part 1 mesh -1 dot nodes. Okay, so I don't think anywhere else I have instances, so I think this piece of code should work to create 99 more number of steps. Okay, so just for the sake of it, save it, name it step creation .py, and let us see if it works. Okay, so we have how many number of steps? We have initial step 1, step 2. So step 2 I don't want to keep, I'll delete it. So we have step 1, so we have only one step, okay, that you can see. Now I run the script, step creation, and there is an error, which is good. Syntax error. What is the syntax error? For I in range. So there is a small problem. Instead of colon I have to have a comma, and save. Hopefully that was the only error. And then file, run script. No. Now what is the problem? File blah blah blah, line 59. There is no step by that name. Why? Why it doesn't have no step with that name? So this is the problem in the first index. So when the value of I is 1, the step 0 is not there. Okay, when the value of I is 1, step 0 is not there. So step 1 is already created. Step 2 we have to start with. So why don't we, so we can start it with 2, or we can simply make it I plus 1 and this one as I, and should work. Okay, so did I save it? Yeah. So file, run script, step creation, another, there is no step by that name. Line 59, what is this in line 59? Is this one only? No. So there is nothing in that step name. So step I plus 1 is not there. That is what I am creating. And the previous step is step 1, right? Oh, I forgot a minus here. I believe that is the case, isn't it? How is this step written? Step -1, no? Step -1, yeah. So minus was missing probably. Okay, hopefully should work now. So these kind of syntax problem keep on coming. So it has worked. Now you see you have from step 2 to step 100 has been created. Step 99 has been created. Okay. So if you have to create so many steps, you can do it by using this code, and you can make, and this piece of coding, how did I make? I didn't know the syntax for this, so I just used the recording system of macro manager of Abaqus, and a little bit of common sense here and there, and you can change the coding to suit your whatever you want to do. And by this way you can code approximately everything what you do in the graphical user interface, including partitioning and sketch making and meshing and everything. Each and everything of the software can be coded using Python. Okay, is it making any sense to you? Do you understand? Okay, all right. So this is it, and so you are going to submit a lab report on this one also. And what you have to do is you have to write what we did and try to do it with a different angle. Okay, so we have done it by dividing into 50 pieces, the outer boundary. So 180 divided by 50 was our angle. So you divide it into 60 pieces, 70 pieces and so on. So change the number of angle and then calculate the boundary condition for that angle and apply that using a Python code. So that will be your assignment and final assignment. And so what you will be submitting is your CAE file. You will be submitting not a text file of lab report. Okay, so for this session you will be submitting a CAE file and your .py file, and you will tell me either in your submission in some way that you have made the model for 60 pieces or 70 pieces or the value of theta. Okay, so I can also check that by opening the Python file, so you don't need to write it, but if you write it, it is okay. And then I will run it and I will see if it is working. If it works, then your assignment is good, you get the marks for that. If it doesn't work for some reason, then you know what will happen. Okay, is it clear? Okay, all right. So if there is any question, if not, then we can end this session. No questions? Okay, good. So that means everything is good. Okay, so okay then, so all the best for your coming exam, and you can leave the session. Yeah, thank you.